So in this amount of time, delta t, given this current density here per unit volume, there's going to be this amount of charge going through that surface. Now, the idea is that we can kind of understand this J here as a volume charge density rho moving with a certain velocity v. Okay, so I have little blobs of charge moving with velocity v in a certain direction. And this current density is just density of charge times the kind of expected velocity around this. So that's the way we would write it. Okay, so that's the case for a volume thing. If I had a line charge or a surface charge, I would have equivalent line charge densities times the velocity, or surface charge density times the velocity. It would be the same kind of thing. Now, so yeah, let's even jump through this. Now, there's a very important conservation law that we need to mention. So charge isn't created or it doesn't disappear. It's conserved. And that leads to a very important relationship between the current density that we have and the local charge density that we have. So let's see how we codify this. So so for a generic surface S, okay, it can be closed, it can be open. The current going through it is given by, well, so let's call this I. So what is this? It's going to be the integral over my surface of my differential surface elements with the current density through it. Okay, so that's really the amount of charge per unit time that goes through the surface. Now, for a closed surface, well, what is this? I have now a closed surface, dA dot J, but by the divergence theorem, I can rewrite that as the integral over the volume enclosed by this closed surface S of the divergence of J. Okay, I'm just again using a mathematical identity, Gauss's theorem, really, to rewrite it like this. Now, if I imagine a closed surface over a tiny, tiny little volume, and I integrate the current going through that surface, obviously this current represents a time, a flow of charge through the surface, therefore a change in the total charge inside that little volume encompassed in there, codified by this closed surface. So this has to equate minus the time rate of change of the charge in this volume V. Okay, and what is this time rate of change of the charge? It's just minus the time derivative of the total charge inside. So what do I get? I get that the integral over this volume d tau of the divergence of J has to be equal to minus the time derivative of the total charge in that thing, which is just the integral over the volume of the charge density. Yeah, this is charge density. as usual. Okay, and just by essentially simple assumptions about smoothness of that thing, this is a function of space and also time. I can rewrite this as just minus the integral over the volume V, d tau, of the partial derivative of the density with respect to time. Okay, I've just inverted the differential and the integral here. Now, since this is true for any volume V, it means that the equality has to occur locally at the level of the integrands in these two things. So that means that I must have locally a relationship between the divergence of my current and the time derivative of the charge density. This has to be equal to 0. And this is a superbly important equation known as the continuity equation. We will do actually a better derivation of that equation once we have seen the Maxwell equations, because it's really a consequence of the Maxwell equations. Here we have derived it a little bit out of the hat with putting in by hand the notion of charge conservation. Okay? It's an equation that should remind you of some others. I guess we'll discuss that more next time, if you have time. We'll get back to this. But you see, so charge conservation means that, well, first of all, conservation, what does that mean? Conservation means that there's a quantity that is conserved in time. There's an object whose expectation value is time independent. What is this object that we're talking about? We're talking about charge. Total charge is conserved. Now, you will probably have heard of Noether's theorem. Have you seen this in classical mechanics? Yes? Okay, so what does Noether teach us? Noether teaches us that the existence of a symmetry is related to the existence of a conserved charge. And therefore, the existence of a conserved charge is also to be related to a certain symmetry. So, and these symmetries are usually manifested in terms of local densities and currents that obey some relationships in there. So that's one form of such a relationship here. The existence of the conservation of charge means that there's a continuity equation relating the time derivative of the local charge with the existence of currents in there that need to pick up the pieces. And I think maybe I'm compelled to leave it here. We will get back to this next time. You haven't seen the continuity equation before, I presume, no? Okay, so then it's going to be an important point for later. Okay, I'll leave it at that for today. We'll carry on next time.